There's a special place in my heart for the dot product. It is really a fantastic math operation. It allows us to encode the law of cosines, the Pythagorean theorem, the distance formula, the equation of a circle, all in one nice, neat little package. And what's great about it is it's easy to do. You don't even need a calculator to get the answer. You can just do it in your head. Before we talk about the dot product, I'd just like to remember some of the basic terminology about vectors. So vectors represent force, and they can be either 2D or 3D, and we write a little arrow over the top of it like that when we're talking about vectors. And then constants, we call them scalars now, and the job that they're doing in this context is to, we're thinking of them as making the vector longer or shorter, rescaling the force. Here's the formula for a magnitude. The magnitude of a vector is how long it is. And then we write this little hat over it here when we mean that it's a unit vector. Unit vectors have magnitude 1. And the way that you produce them is you take a vector and you rescale it down by the magnitude. So whatever the magnitude was before, you divide by that, and that rescales it down to be magnitude 1. Sometimes we call them direction vectors as well. Here's a brief example. I picked this 3, 4, 5 triangle. And so then I got a magnitude of 5. And then here is what we would call the direction vector, or a unit vector in the direction of v. And all you do, I think it's transparent, right? All you do is just take the coordinates and divide by the magnitude. The dot product of two vectors is a scalar, so it's a way to combine vectors and end up with a number. Sometimes you'll see people call it the scalar product for that reason. And what you do here is how you write it in English, the sum of the products of the components. So if that jargon doesn't make sense to you, look at how the math works. It's really easy. So it's literally this simple. You just do 2 times 5 plus negative 1 times 3. So 2 times 5 is 10, and negative 1 times 3 is negative 3. So 7. So that's the dot product of the vectors u and v. You write that little dot in between them, the dot product. Okay, I put it at the bottom of the page, but this is actually super important fact about the dot product. This is what it makes it useful. The first one is it's easy to do, right? I mean, it's just a no-brainer. You just multiply the numbers and you add them together. And then the useful thing is that also gives you the right side of this equation, which is the magnitude of one of the vectors times the magnitude of the other vector times the cosine of the angle between them. So let's do an example where we use this to find the angle between some vectors. So I use the same vectors as from the previous example because I'm lazy. And then I ask us to find the angle between the two vectors, and I'm going to use this dot product formula in order to figure it out. So the nice thing is we've already worked out the left-hand side of this equation. So those two pieces, we don't know those yet, and we also don't know that one. So let's see if we can find the missing pieces in this formula. So I need magnitude. So the magnitude of u will be the square root. I also need a magnitude of v. And now let's plug everything into this theorem about the dot product. Okay, so I worked out the dot product already. I got 7. And then the magnitude of u, that was the square root of 5. And then the magnitude of v was the square root of 34. And then the cosine of the angle between them. So what this means is that the cosine of the angle between these two vectors is 7 over the square root of 5 times the square root of 34. So cosine inverse here is going to give me the angle between these two vectors. Be careful what mode your calculator is in. So since this is a math class, I'm going to leave it in radian mode. So the cosine inverse of 7, the the cosine inverse of 7 divided by, now be careful because you have a product in the denominator. I'm going to need to put that in parentheses. So the square root, which makes another parentheses of 5 times the square root of 34. Okay, and then close the square root parentheses, and then close the denominator parentheses, and then close the cosine inverse parentheses. And I got approximately 1 radian. I'm going to switch it to degree mode. And then I should just be able to push second enter and it'll bring it up again. So I got about 57.5 degrees. This is really a phenomenal result. I mean, if you look at what we've done here, at the end of this, I have done something that is really a geometric process. I've really measured the angle between two vectors. And at no time did I ever do anything geometric. I never got out a protractor. I never drew any pictures. All I did was use the magic of this dot product formula. It's kind of fantastic, and it really makes me wonder, where does this come from? Where are they getting this sum of the products formula, and how does it somehow produce some kind of cosine? The easiest way for me to understand the dot product and where all of this magic comes from is by trying to connect it back to the Pythagorean theorem. So if you just think about what the Pythagorean theorem is doing, it's just a squared is really just a times a plus b squared is really just b times b. So all we're doing now is asking ourselves, what if we allowed these two a's to be different? What does that give us? And it turns out it gives us exactly this thing right here. So the result is that this gives us the magnitude of u times the magnitude of v times the cosine of the angle between them. I think it's really useful to try to use the law of cosines and vector subtraction in order to verify this fact. Maybe I'll make a video on it later, but if you really want to feel like you understand how this works, that's probably worth your time to take a few minutes and just try to prove this fact to yourself. Like this name orthogonal, it's kind of a fancy word. It just means perpendicular. You're also going to see people use the word normal when they mean perpendicular. So remember that if the angle between two vectors is pi over 2, then the cosine of pi over 2 is 0. So here, again, I have two vectors, u and v. I forgot the little vector on top of that one. And then if you calculate u dot v, you're going to get negative 30 plus 30, which is 0. So this means u and v are perpendicular. So this gives us another way to write the equation of a line. So suppose this dotted line here is L and u is a vector in the line. And suppose that v, I really want to call it n for normal, but let's call it v here for normal vector. So just get used to this. That also means perpendicular. That also means orthogonal. So there's just more than one word for that. So you got a line, you got a vector in the line, and then you have a vector that's normal to the line. Then u dot v must equal 0 in order for us, because of this fact about dot products and perpendicular vectors. So we're going to write the equation of a line. We're back in college algebra. Here I've given us a vector that is normal to the line, and I've given us a point that is on the line, and we are asked to write the equation of this line. So what we need in order to use this fact about dot products is a vector that is in the line. So what I'm going to do is let's let xy be a point on the line. I can produce a vector that is in the line using final minus initial. So I'm going to view xy as the final point on the line and 5, negative 1 as the initial point on the line. So then x minus 5 is equal to, and y plus 1. Now I've done it. I've got a vector that is in the line using final minus initial. So since v is perpendicular to the line and u is in the line, I know that the dot product of these two vectors must be equal to 0. So v dot u equals 0. What does that look like? That means that here are the coordinates, right? I just need to multiply those two and multiply those two and then add them together. So I get 2 times x minus 5 plus 3 times y plus 1 must equal 0. And I've done it. There it is. So it's kind of fantastic. It's fun to use dot products. Here's a new way to solve writing the equation of a line problem. Okay, it's kind of like, well, great, teacher, why is this better? I'm already good at writing equations of lines. The reason that this is really good is because this method generalizes to 3 dimensions better. So now we can use this technique, and instead of having a vector that is normal to a line, I can have a vector that is normal to the plane. So that's what this technique is for. Projections are a really common application of the dot product to physics, and we use this concept a lot in this class. So what's the idea? Suppose that this is like supposed to be a wagon. This is my drawing of a wagon, and you're not pulling the way that the wagon is going. You're kind of pulling at an angle. So I'm going to name that angle theta right there. Then not all of the force that you're using is pulling the wagon in the direction that it's going. Some of the force is pulling the wagon up. It's just making the wagon lighter. So what you want to know here, the concept of a projection is it's the actual amount of force that's going in the direction of motion. And the way that you calculate that is you just drop this perpendicular down right there. And this length right here is called the projection onto you. Okay, let me clean this up a little bit. Actually, the length is called the scalar component of f onto u. This actual vector right there that goes from the origin of f out to however far you would go if you dropped that perpendicular down, this is the projection, is that vector right there. And then the length of that vector is called the scalar component of f onto u. So we're gonna use the dot product to figure out this scalar component. So let's just call it p for now, just for projection. See, I didn't put a little hat over it because right now I'm just talking about the scalar component. So from right triangle trigonometry, the cosine of the angle between them is equal to the adjacent over the hypotenuse. The hypotenuse is the magnitude of v there. So what this means is that the projection is equal to the magnitude of v times the cosine of the angle between them. This is so close to our dot product formula, so let's just write down the dot product formula and then solve for this term right there, and that will show us how to use the dot product in order to calculate these scalar components. Now, since the dot product is just the magnitude of u times the magnitude of v times the cosine of theta, and this thing that we're looking for here, the scalar component, is just the magnitude of v times the cosine of theta, I'm just so close. Right here it is, and then there it is right there. So if I can just get that by itself, then I'll know how to calculate these projections. So I'm just going to divide both sides of this equation by the magnitude of u. So u, and then I'll put a 1 over magnitude u out front here. And then dot product with v, this is going to be equal to the magnitude of v times the cosine of theta. Okay, so I can actually simplify this because this right here, a vector rescaled down by its magnitude, is actually just a unit vector in the direction of u. So this is my formula. This is the cleanest way to see it, in my opinion. So this is what I do. If somebody asks me to find the component of v in the direction of u, what I do is, in the direction of u, I turn u into a unit vector. That means I turn u into a direction, and then I just calculate their dot product. So a lot of the magic behind how powerful dot products work and how well they work is because what's really going on is they are a way of calculating projections. Let's do an example of this. But really fast, before we move on, I should explain also, sometimes we're concerned with what the length of the projection is, and sometimes we're actually concerned with the vector whose length is that scalar component but points in the direction of u. So all I need to do so this is how long I want the vector to be, and I just want a vector of this length that points in the direction of u. So that's easy. All you need to do is just take this, remember this is a scalar, and then now just multiply that by u hat, and you will get a vector that has the magnitude that you want. You want the magnitude to be that. And then now you just rescale the unit vector because that's the direction that you want the force to be pointing in. So people will also call this the vector projection of v onto u. There's special notation for this. You'll see PROJ for projection, and then they'll write a subscript, a little tiny u, because that's what you're projecting it onto. And then inside the parentheses, you put the vector that you're projecting. So this is the projection of v onto u. Let's do an example. Let's find both kinds of projections, the scalar projection and the vector projection, and I've cooked up a couple of vectors here. So what I'm trying to do is project v onto u, and the way that process works is anytime I'm trying to project onto a vector, I always turn that vector into a unit vector. So the first step here is to turn u into a unit vector. The way you do that is you find the magnitude of the vector and then rescale the vector down by its magnitude. So I found the magnitude of u, and then it would turn out to have magnitude 3, and then I just rescaled u by a factor of 1/3. And now all I need to do is find the dot product of u hat and v, and that will tell me the scalar projection of v onto u. Okay, so dot products are easy, right? I mean, I just multiply the components and add everything up here. I did it and I got 5/3. So the component of v in the direction of u was 5/3. Now to find the projection onto u of v, what I'm going to do is just take that 5/3 and multiply it by u hat. So it's just going to be 5/3 times this whole vector right here, -1/3 I plus 2/3 j plus 2/3 k. So I got -5/9i plus 10/9j plus 10/9k, and there we've done it. That is how awesome the dot product is. It lets us solve this physics problem. I mean, I think in terms of relative difficulty, this has got to be, a pretty easy process, especially considering how massive the application of this process is. It makes sense to me that work is force times distance because if you have to push harder, then that's more work. And if you have to push over a bigger distance, then that's more work. So now let's use the tools of vectors in order to calculate work in a situation when the force that you're using is not in the same direction that the object is moving in. So in order to calculate the actual amount of force on the object, we're going to have to use the concept of projection. So the actual force that you're pushing, that you're using to move this handcart along the path, is going to be the projection onto d of f. D here is the displacement vector. And then you're going to have to multiply that by the distance that you have to move. So this is going to be the magnitude of d. That length right there is how far you have to move it. Okay, so to calculate the projection of f onto d, what I need to do is d hat dot product with f multiplied by the magnitude of d. Now remember, d hat is just d over the magnitude of d, dot product with f, and then I have another magnitude of d out here at the end. So these are going to cancel, and we just end up with this great formula. The way that you calculate work, if you're using vectors, is just f dot d. So another really awesome thing that the dot product does, it also calculates work. Let's do it. Suppose that we are using a force 3, 2, and we're trying to move an object from 0, 0 to 5, 7. Then I'm going to calculate the displacement vector here. I'm just doing final minus initial, so 5 minus 0 is 5, and 7 minus 0 is 7. And then the work is just going to be f dot d, which is 3, 2, dot product with 5, 7, which is 29, and the units of work, the scientific units of work, are joules. So this force did 29 joules of work to move this object from 0, 0 to 5, 7. I've been a little bit of a bad math teacher here. I've been using these properties of the dot product without mentioning them, so please forgive me. I do think it's important that you understand these algebraic operations and properties here because we use them a lot. So one of them is the dot product is commutative. It doesn't matter which order you do them in. U dot v is the same as v dot u. Be careful with that because there are other things that are called products that don't have that commutative property. You know, this one is essential, though. It better distribute over addition. So this is a statement about dot products distributing over addition. Of course, if you dot product something with 0, you should get 0. You know, you can reassociate where the constants go. And then actually, bullet point number 4 here is really important. Let's just look at this. When you do u dot u, you do get the magnitude of u. So just as a final thought here, what I want you to do is go check back in the notes where we talked about a generalized Pythagorean theorem and try to make sense out of bullet point number 4 here as really being the Pythagorean theorem.